Hello everyone, my name is Roger and I'm now going to present my final project on training a centralized reinforcement learning policy for a multi-agent complex real-time strategy game. So there have been many great successes in applying multi-agent reinforcement learning in complex strategy games, arguably the most impactful ones being DeepMind's work on StarCraft and OpenAI's work on Dota, that showed how it's actually feasible to train multi-agent RL from scratch in such complex environments. And recently, more affordable environments have appeared that pose a very similar set of challenges as the last two, mostly in terms of the size of the action space. That's now a joint action space and dynamic depending of the units that are in the game, and also the sparsity of the reward distribution, because in the end, in these 1 versus 1 games, the only thing that matters is winning or losing. They are also multivariable optimization problems in which the agents need to gather resources, control territory, and coordinate units, among others. And there's also non-stationary reward and transition functions. So in the end, the agent's experience is also a function of the actions taken by the opponent. So in this work, I use this one in the middle, which is the Lux V2 environment. So in this project, I propose a centralized policy that's an encoder-decoder policy that takes a set of input feature maps and encodes them using residual networks, and then there are two actor heads, one for the factories and one for the robots, and a critic head. So in the end, this is an actor-critic policy. Some highlights is that I use the squeeze and excitation layers in the encoder, which allow to learn the dependencies between feature maps, which otherwise are assumed to be independent. I also use this encoder-decoder architecture, so the actors are a stack of transposed convolutions, and during training I perform invalid action masking to prevent the model from learning from actions that are not going to be executed in the game because they're illegal. I also use reward shaping, so I don't train with a sparse reward, and I also use self-play, in which my agent is trained playing against a pool of opponents that are previous checkpoints of the agent itself. I trained this architecture using PPO, which works by collecting a bunch of trajectories of on-policy data, computing the reward to go, estimating the advantages with a value head, and then training the actors to maximize these advantages using a surrogate objective, which prevents the policy to change too much before after each training step, and then the value function is trained as usual by regressing the reward to go. And first I perform a hyperparameter sweep in which I find a final configuration that I train for multiple days using 8 GPUs in parallel, in which I can see that the reward distribution is actually maximized, the tens one, and then the episode length also gets to the 1000 in many cases, which is the maximum steps in this game, which is a very complicated goal, and it's a great achievement because the resources in this game are very sparse, and if the agent doesn't master the skill of actually gathering resources, it won't survive for longer than 100 episodes. So this shows how the agent is actually being able to learn, although there's high variability. Depending on the map, the agent just fails to gather the resources. Then here's another example of the final configuration in which it performed very well in the beginning, but then in a specific training update, the KL between the previous and the current policy was too big, and it basically forgot everything that it learned. This happened at day 3 during training, which is very annoying, but it's things that happen when using PPO. So I'm gonna end this presentation with these 2 videos of my best agent during training playing the game. So thank you very much.